So this lesson is on mutually exclusive events. Mutually exclusive events are events that cannot occur at the same time. So for example, turning left and turning right are mutually exclusive because you can't do both at the same time. Tossing a coin, heads and tails are mutually exclusive. If you're rolling a die, getting a 4 or a 5 with one roll would be mutually exclusive because you can't get both at the same time. So examples of events that are not mutually exclusive would be like turning left and scratching your head at the same time. So those can happen at the same time, so those are not mutually exclusive. Driving and texting would be an example of events that should be mutually exclusive because they shouldn't happen at the same time. Yeah, relating this to probability, let's do an example. Terry attends a fundraiser at which 15 t-shirts are being given away as door prizes. Door prize winners are randomly given a shirt from a stock of 2 black shirts, 4 blue shirts, and 9 white shirts. Terry really likes the black and blue shirts, but is not too keen on the white ones. Assuming that Terry wins the first door prize, what is the probability that she will get a shirt that she likes? So to be consistent with the way we've been solving our probability problems, we're going to label our events. So event A would be her winning a black shirt. And event B would be her winning a blue shirt. So Terry would be happy if she won a black shirt or a blue shirt. It doesn't really matter which one. So first thing we want to do is maybe calculate the probability of her winning a black shirt, and then calculate the probability of winning a blue shirt, and then adding those, right? Because it's an or, that means plus. She doesn't care if it's black or blue, so we're going to add up the probabilities of each, and that'll give us our total probability. So probability of winning a black shirt, so event A happening, would be, we said there were 2 black shirts, so it would be 2 out of, how many shirts do we have in total? 2 plus 4 plus 9, it just says 15 at the beginning. And then probability of winning a blue shirt would be, how many blue shirts are there? 4. So it would be 4 out of 15. So now your probability of A or B happening would be 2 out of 15 plus 4 out of 15. And that gives us 6 out of 15. And we can reduce that to 2 out of 5, which is equal to 40%. So she has a 40% chance of winning a shirt that she likes. So in this example, just to recap, event A and B are mutually exclusive events because they can't happen at the same time. So she can't win a black shirt and a blue shirt at the same time. It's going to be one or the other. So in this case, they're mutually exclusive. So now let's look at the rule for solving the probability of mutually exclusive events. So if A and B are mutually exclusive events, the probability of A or B occurring would be the probability of A plus the probability of B. So just to illustrate this, I'm going to just draw a Venn diagram here. We have, this is A, this is B, and we know by definition that the intersection of A and B is obviously going to be 0 because they're mutually exclusive. So they can't happen at the same time, which means there's no overlap. So that means that your outcome would either be in event A here or in event B, which is here. Now let's look at an example that deals with 2 non-mutually exclusive events. An electronics manufacturer is testing a new product to see whether it requires a surge protector. The test showed that a voltage spike has 0.2% probability of damaging the product's power supply, a 0.6% probability of damaging downstream components, and a 0.1% probability of damaging both the power supply and the other components. Determine the probability that a voltage spike will damage the product. So of course, first thing we want to do is define our events. So event A would be damage to the power supply. And event B would be damage to all the other components. Okay, I'm going to draw a Venn diagram to illustrate this. So this is event A, this is event B. I made it overlapping because in the question we have a 0.1% chance of damaging both the power supply and the other components. So that would be this middle section here, the overlap, and that would be 0.1%. And then for probability of A, so damaging the power supply, we have a 0.2% chance and 0.6 for all other components. Now, if we remember from chapter 5, the middle component is actually counted in both A and B. So here we want to figure out just this and this to figure out what is the probability that the product is going to be damaged. And the 0.1% is being overcounted, so we're going to have to compensate for that somehow. So the probability of A or B happening in these two non-mutually exclusive events would be the probability of A plus the probability of B, and then we need to subtract the probability of that middle section, A and B, or A intersecting with B. So now let's go ahead and solve that. So this is equal to probability of A is going to be 0.2. Probability of B is 0.6 minus the middle section where they occur together would be 0.1. And that gives us 0.7%. So just to sum up what we just did above, the addition rule for non-mutually exclusive events, when you have A or B as your events and they're not mutually exclusive, you would just add up the probability of A to B and then subtract the intersecting section. So the probability of A and B. Okay, that's it. Hope you took notes.